Apparently everyone is unhappy how hard the midterm was, and at the same time, everyone wants to keep the final exam as hard as the midterm. That's the situation we have. It was like 80-20 last time I checked. Okay, so in the last session, I talked about a bunch of algorithms for strings, and we especially talked about the algorithm on finding substrings or pattern matching. So let's say I've given you a really large string. So my input is, let's say, a string S. And I'm assuming that this is a huge string, really long. And let's say that I also have a pattern, which is a much shorter string, maybe. And let's call this one T. And the question, of course, is T a substring of S? Is T a substring of S? We already know how to solve this using suffix trees. So I can just create a suffix tree of S, and then T is a substring of S if T is a prefix of a suffix of S. And then I can basically use the suffix tree to check this. So if I have the string S which has length n, and if my string T has length m, I already know how to solve this in O(n plus m using suffix trees. Okay. And again, this is asymptotically optimal because, as usual, this is the most common optimality argument you'll see in this course. I have to read the input. And just reading the input takes n plus m time. So I cannot do better than what suffix tree, at least up to a constant factor. Okay. But today I'm going to show you some simpler ways of achieving the same time. And you might wonder why I first taught you about suffix trees, because if I first teach this, you will not listen to the suffix trees. And suffix trees are actually more powerful because they're online and so on. And I don't really expect you to remember O'Connell's algorithm completely. As long as you know how to use the suffix tree, you're fine. So whenever you want to implement O'Connell, just Google it, you'll find it, and you'll implement it, right? Okay. But today we're going to see basically simpler solutions for the same question, but of course our runtime is not going to improve because there is no way to improve this. Okay. The first thing, or the first algorithm we want to see is the Rabin-Karp hashing, or Rabin-Karp pattern matching, let's call it. So the idea here is really simple. Let's say you want to compare two objects, and these objects can be anything. They can be strings or whatever, but these objects are huge, right? So normally comparing them will take a lot of time. So going back to our very first problem, if I give you a bunch of strings and I give you another string and ask you, is this in the first set of strings that I gave you? You can't just go ahead and compare all the strings. Even if you put them in a binary search tree, every comparison is now taking OK time, where K was the length of the strings, right? So the idea in Rabin-Karp is very simple. Let's just make it so that the comparisons take much less time. Now, generally speaking, if I have two strings, and let's say I have a string that is 1 GB long, there's no way I can compare it with another string in O1, right? But I can create maybe some sort of a hash of this string or a digest of this string. So generally, suppose that I have a function f, and let's say that this f takes a string, and this is a string of any length, right? And then it just gives me values from a very particular and small domain. So let's say that it just gives me unsigned integers. And let's say these are 32-bit unsigned integers. So I can just think of them as sequences of 0 and 1 of length 32. Okay. What I'm saying here is consider any function f like this. Now, what can I know for sure? Suppose that I have two different strings. Let's call them A and B. So if f of A is not equal to f of B, then I can be sure that A is not B, right? It's just the definition of a function. But if f of A is equal to f of B, I don't know, right? Because I don't know if my function is one-to-one, and well, most likely my function is not one-to-one, because on the right-hand side, I have a finite codomain, finite range. On the left-hand side, I have an infinite domain. So it's actually impossible to have a function f like this that is one-to-one. So there are definitely going to be two different strings, A and B, such that f of A is equal to f of B. Okay. But if I can compute the values of this function f really fast, then I can already have a heuristic, right? And my heuristic is that, again, let's say I have a set of strings. I want to ask if a new string is in this set. I can just compute the f values of all the strings in this set, and I can put those in a binary search tree, in a balanced binary search tree. And then when I see a new string, I first compute its f value, and then check, is this f value there? Is it already in my set? And if the f value is not already in my set, I know that this is a new string. I know that I haven't seen this string before. If the f value is in the set, I don't know anything. I have to go and actually check. I have to see, like, from the strings that had that f value, is any of them equal to the string that I'm trying to add? Okay. So this is not very good for us, because we're getting information in only one of the cases. And by the way, we call these functions hash functions, but they're very different from the hash functions used in cryptography and other things. So I would just rather call them functions most of the time. Now, suppose that instead of just having one function, I have a family of functions. So I want to make my algorithm randomized. I want to say I have 1,000 different functions, and all of these functions are easy to compute. But then at the beginning of my algorithm, I'm just going to randomly pick one of them. Okay. So instead of saying that I have one function f, I say I have many functions fi, and every function is basically a function that is taking a string and giving me a digest or a hash, whatever, it's giving me 32 bits, right? Now, again, if I have two strings that are equal to each other, if x is equal to y, then of course, fi of x is going to be equal to fi of y. Okay. But the other thing that I want to say is that if I have two strings that are not equal, if x is not equal to y, then I want to say the probability that their hashes happen to be equal is actually small. Okay. So if this is the case, I want to say that the probability that fi of x is equal to fi of y is less than some epsilon. Okay. Now, what is this probability over? What is my distribution? It's basically, I had many different fi's. I'm picking one of them randomly. Okay. So I have many different hash functions. Let's say I have a family big F, which is F1, F2 to, I don't know, FR, let's say. And at the very beginning of my algorithm, I say I is basically a uniform random number between 1 and R. So at the beginning of my algorithm, I'm just going to pick and fix one of my hash functions. And then I'm going to say, in the entirety of my algorithm, I'm just using this function. And the two properties that I want to have are these two. The first one is, of course, always there, because that's just the definition of a function. If x is equal to y, then the value of the function at x should be equal to the value of the function at y. But if this big F is a good family of hash functions, then I would hopefully have this one as well. Okay. Now, in this course, we are not really going to get into how to create hash functions. I'm going to give you some examples of hash functions that work well in practice, but creating good hash functions and like families of hash functions with good epsilon values, that's a lot of number theory. Okay, so suppose that I have this. How can I actually use it for my problem, for my pattern matching problem? So let's just look at the naive algorithm. Let's say that I have this S, I don't know, A, B, A, C, let's say. And let's say that I'm looking for a T, which is A, C. Okay. What does the naive algorithm do? The naive algorithm basically takes 2 pointers, one on the first string and the other one on the pattern, and tries to match. Okay, so let's say this is, I call this one I call this one J. So I check, is SI equal to TJ? If it is equal, I would just increase both I and J, right? So I will go here, J will go here. Then I do it again. Are they equal? Yes, they're both pointing to A's. So I increase the pointer here, and I also increase the pointer here. Are they equal? Yes. So I increase again. Now at this point, I ask, are they equal? And they're not equal. Okay. When I get a mismatch like this, what does the naive algorithm do? The naive algorithm just says, okay, let's go back to the beginning of T. And also, let's ignore everything that we have matched in S, and let's go back here, right? So I couldn't find T starting at index 0 of S. Let's see if I can find T starting at index 1. And it again starts matching and going forward until it gets to one mismatch. And then it says, let's go to the beginning of T, and let's go to index 2 of S, and so on. Okay, so this is actually terrible, because basically, it's going to take O and M time in the worst case. And it's actually easy to come up with instances where it takes omega and M time as well. So this is actually theta and M in the worst case. Okay. Now, what is the problem? The problem is that for every possible starting point, I'm looking at strings of the same length as T. So here, the length of T or M is 4. So I'm looking at this string, the string of length 4 that starts at index 0. Then I'm looking at this string. Then I'm looking at this one, and so on. So I'm looking at all the strings, all the substrings of length 4. And I'm constantly asking, are these equal to T? But I have no good way of checking, right? The way I'm doing the checking is just a naive thing. So I'm looking at each one of these substrings. I'm comparing it with T, one character at a time. So I'm looking at n substrings, and each of them have m characters. So I have to compare m characters between each substring and T. That's why it's taking nm. Okay. But now I can use this idea of having a hash function to actually make this faster. So here's what I say. I say first, compute the hash of this pattern T, so that you know what hash you're looking for. And then for each one of these substrings, compute its hash first and check if the hashes match. If the hashes don't match, the strings are definitely not the same, right? And I don't have to actually go and compare the strings. If the hashes match, then the strings may or may not be the same. But in that case, I can just go and do the naive thing and check them character by character. Okay. So this is my algorithm, and well, actually, the Rabin-Karp algorithm. Given S and T, it just says this. It says that let H be the hash of t. And remember that my hash was some fi. And again, I've chosen a random hash function at the beginning of my algorithm. Okay. And then it says for every starting point, for I from 0 to what is the maximum that it can get? Well, let's say n minus m, right? Maybe there's a -1 + 1 there. Just find the hash of the string s, but only the substring that starts from index I and has the same length as t. Okay. What is that? That's from index I to index I plus m minus 1. Okay. Okay, so if I add this to this, I would get the m's cancel out. I would get n minus 1, which is correct. Okay. So calculate that hash and then just check if the two hashes are equal. So if these two hashes are not equal, then I know that I definitely don't have a match. If they are equal, if h is equal to h prime, then do an actual match. Then check whether t is equal to this substring, to s from index I to index I plus m minus 1. And if it is, then just return I. So we're just returning the index of the first occurrence of our pattern. And if they're not equal, and if you don't find anything until the end, you would just return something like, I don't know, return null or return -1, which means that you didn't find t. Okay. So this is a very simple algorithm, of course. Several issues. The first issue is whether this algorithm is always correct. Well, that's pretty easy to prove, right? Because if t appears somewhere in S, then one of these substrings, S from index I to I plus m minus 1, is going to be equal to t. And if it's equal to t, it's going to have the same hash. So the hashes are going to match, and then I'm going to check if they are actually equal, and I'm going to return that index. And also, there is no way I would return something wrong here, because before returning, I'm always checking that the strings are the same. So that part, the correctness is easy. The more complicated part is the runtime. What is my runtime here? Look, I have this for loop here, which is going from 0 to, well, let's say at most m, or n, sorry. So that's O(n). Okay. But then inside this for loop, I'm constantly computing these hashes. And also I'm computing one hash out there at the beginning. So this is plus all the time taken for the hashes. Whatever it is, we will get to it. Plus the time that it takes when the hashes are equal to actually check whether the two strings are equal. So these are two strings of length m. So checking this equality here, this one is actually OM. But how often are we going to call it? Every time that I get here, well, once I'm going to call it for the actual match, right? So that's once. But how often would I call it by mistake? There is only a probability epsilon that the hashes match if the strings don't actually match. But I'm doing this n times. So it's at most, let's say, n epsilon. I'm just using the union bound here, times m. So it's actually n epsilon plus 1 times m. So let me just add a plus m at the end as well, because when there is a match, I'm going to actually do it anyway. So no matter how small you make the epsilon, you have the case where it actually matches. And this is basically the extra effort that you're putting in, the expected extra effort that you're putting in. So let's say expected runtime. for all of the things that had the same hash but didn't actually match. So first of all, what should I put for my epsilon? What do I like my epsilon to be? If it's 1 over n, it just cancels out with the n, and it gives me 1, right? So the first thing is make sure you choose your family of hash functions in a way that epsilon is almost 1 over n. Okay. So if that's the case, then the next problem is the hashing time. How much time am I spending calculating all these hashes? So look, when I'm calculating the hash of t, again, the same argument as before, I have to go over t, and t has m characters. So calculating the hash of t should take OM time, even if I have an optimal hash function. And then I'm doing this over and over again. I'm doing it n times for different strings of length m. So it seems that, well, I can get probably a hash function with runtime ONM, and it seems I cannot do better because, well, that's, I have to go over my strings, right? Well, not really. The strings that I'm looking at are actually pretty related to each other, right? So this is what's happening. Let's say I have my big string S. Let's say this is S. And I also have my small string T, my pattern. Okay. So of course I have to calculate the hash of T. And I do that. So this is like Fi of T. But what are the other strings that I have to compute hashes for? They're basically all the strings that have the same length as T and are substrings of S. So I have to look at this string. I have to then look at this one, which is just the previous one, but with 1 character forward, and so on. I have to look at this one, and so on. So these are not completely independent strings. Each one of them differs from the previous one in only 2 characters. It's just, if I want to go from this one to this one, I'm just removing 1 character from the beginning and adding 1 character to the end. So if I have a hash function such that I can find the hash of this second string based on the hash of the first string in constant time, then the total runtime I'm spending on my hash functions is also going to be ON. And if that happens, then all of this is linear time. It's ON plus M, basically. Okay? So what I need is actually what we call a rolling hash. A rolling hash is basically a hash such that given, let's say, the hash of the string S from index I to index J, it is easy to compute the hash of the same string. Well, sorry, not Fi, just F. The hash of the same string from index I plus 1 to index J plus 1. If my hash function has this property, I say that it's a rolling hash. Now, what does it mean for it to be easy? Well, for this particular use case, I mean that you can do it in constant time, in O1. Okay? So suppose that I have given you the hash of the substring from index I to J, and I'm asking you for the hash of the substring from index I plus 1 to J plus 1. They are different in only 2 characters. This one doesn't have I, and instead has J plus 1. Right? Okay. Now, how do you create a rolling hash? I'm just going to give you one way of creating rolling hashes, but in practice, you can use whatever rolling hash that you want. So Rabin-Karp doesn't really specify what hash you have to use. You can use whatever hash function you want. This is just the hash function that most people use. And I'm also not going to prove to you how you can get this epsilon to be small. Okay. So let me use the same notation as Wikipedia. Yeah, they called it A and K. Okay. So let's say I have a string. Let's say my string S consists of a bunch of characters, C1, C2, C3 to CK. Okay. I'm going to say that I pick some number A. I don't care what A is at this moment. Just imagine that A is an integer. And I'm going to say when I want to calculate the hash of this S, I'm just going to do this. I'm going to look at this S kind of as a number in base A. Okay. What does this mean? I mean that I want the hash of S to be something like this: C1 times A to the power of K minus 1 plus C2 times A to the power of K minus 2, so on to CK times A to the power of 0, which is just 1. Okay, so this is how I want to calculate my hash. I want to say, consider this string of characters C1 to CK. Remember, every character, I mean, it has an ASCII code or a Unicode code. What's the weird thing to say? So this is, every character is basically a number. I can look at it as a number, right? And then I can look at this whole string as a number written in base A for whatever A that I choose. So I can say that the hash is basically that number. Now, of course, the problem is that I wanted my hash to be small. And this is pretty big. So how do I make it small? I can just take it modulo some other number. So I don't just pick A, I also pick some other number. So I pick two numbers, A and U. And then I say that the hash of this string S is just looking at S as a number in base K. But because this number can get big, I'm going to take this modulo U. And now I'm sure that all of my hash values are between 0 and U minus 1. So now all of my hash values are small. Okay. But do I have this rolling hash property? So let's say that I have some string. Okay. And then I have another string which just doesn't have the first character, but instead has a new last character. Okay. So there was C1 here, let's say, C2 all the way to CK. And this one starts with C2. It doesn't have the C1, but it doesn't end at CK. It also has a CK plus 1. And let's say that I have the hash of the first one, and I want to find the hash of the second one. Okay, so let's call it, well, I've already called this S. Let's call this one S prime. So I know f of S. Okay. Now, what is f of S? It's C1 times A to the power of K minus 1 plus C2 times A to the power of K minus 2, so on, to CK times A to the power of 0. So the first thing I want to do is to get rid of this C1 at the beginning. So I just take f of S and I subtract C1 times A to the power of K minus 1. Okay, so f of S minus C1 times A to the power of K minus 1. Now, I don't have the C1 anymore. So this is fine. But now when I'm computing the hash of S prime, this C2 should actually be multiplied by A to the power of K minus 2. Right? But previously, sorry, by A to the power of K minus 1. But previously, it was multiplied by A to the power of K minus 2. The next character has to be multiplied by A to the power of K minus 2, but it was multiplied by a lower power of A again. And so on until I get to CK, which was previously multiplied by A0, but now it should be multiplied by A1. So if I take all of this expression that I had, and I just multiply this by A, now all of these characters from C2 to CK are multiplied by the correct powers of A. Okay. Finally, I have this CK plus 1, the new character, which has to be multiplied by A0, which is basically 1. So I just add it, plus CK plus 1. Okay. And this whole thing gives me the hash of S prime. And very importantly, this can be calculated in O1, right? Because I can pre-calculate a to the power of k minus 1. And then I can just do one subtraction, multiplication. There's another multiplication here and an addition here. And of course, all of these things are modulo this number u. Okay. So if I use this kind of rolling hash, I finally have a really good runtime for my Rabin-Karp algorithm, right? Because so first I have to find the hash of t, but finding the hash of t is easy. I just use the formula here. Just go over this, calculate all of it. That gives you the hash of t. And then here, you have to find the hash of the prefix of s that has the same length as t, the prefix of s of length m. You find that, and that's going to take OM time. But immediately after you find that, in every next iteration of this for loop, you just need to use the previous hash to find the current hash. And that's just this part. It's O1 time. So my total runtime, my total expected runtime, would just be On plus m, because my hashing time is now On plus m. This epsilon was chosen such that it cancels out the n there, and I have like n and m there, so it's On plus m overall, which is great. It's basically, again, optimal, but this is easier to code, hopefully, than a suffix tree. But note that this is not worst case runtime, this is expected runtime. So if you want to do a worst case analysis of this, you might get really unlucky and you might get a nasty input that doesn't really work with your particular hash function. And every time that you compute the hashes, they might be equal. And then you might get a worst case runtime of On times m. Doesn't really happen in practice that often. But also remember that this expected runtime was over the choice of the hash function from our family of hash functions. So, but here I just talked about one hash function. How do I have a family of hash functions? Well, pick different values for a and u. Now, in practice, when we implement this, usually u is just 2 to the power of 32. Because if you just save this number as an unsigned integer in C++, it just does the modulus part automatically. So you can just do the multiplication and addition and subtraction and all of those. So normally when I implement it, I don't put the u in there at all. But you have to be very careful to use unsigned integers. If you use just normal integers, it wouldn't work. And you have to do the modulus on your own. And for the a, it's good practice to use prime numbers. So just have like 10 prime numbers hard-coded into your code and pick one randomly at the beginning of your code and use that as a. This was pretty easy. Let's now look at an algorithm that doesn't use randomization. And by the way, one point for people who do competitive programming, a lot of the times in competitive programming, people just use one fixed value of a. And when you do that, it makes it terrible because now I can go and find test cases where the hashes are always the same, right? So if you hard code the value of a, I can always find a bad test case for you. But if you have randomization in a, then that wouldn't happen. Okay. Now, the next algorithm I want to talk about is the KMP algorithm. I hope I write this correctly. Knuth-Morris-Pratt. These are the people who came up with this algorithm. Again, our problem is exactly the same as before. I have a long string S. I have a pattern T. The question is, does T appear in S? Of course, I can also extend it to say, if it appears, return the index in which it starts or it ends, or if there are several appearances, tell me how many and where and things like that. But I'm just going to consider the simplest format of this question. So I just want to return true or false. Does T appear somewhere as a substring of S? Let's say S is something like this. And actually, let me first do my T. Let's say this is my T, 4 A's followed by a B. Okay. And let's say that my S is just a bunch of A's and then a C and then 4 A's and then a B. Okay. I'm doing this so that I give you a terrible example of how the naive algorithm can really stop working. Okay. Now, let's say I'm doing the naive algorithm. The naive algorithm would just look at prefixes of length 5 here and try to match them. So I would first look at this prefix and I'll try to match it with this one. So if you look at the pointers that I have on them, I check that this A matches this A, then this one matches this one. I'm happy, I'm going forward. This one matches this one matches this one, and now I have a mismatch. Okay. But now the naive algorithm doesn't remember that I have seen so many A's and all of these A's match those previous A's, right? So it doesn't really make sense to go all the way back. But that's what the naive algorithm does. The naive algorithm says now you have to go back here in S, start from the second character of S, and you have to go to the beginning of T and try to match again. Even though I have already seen that all of these A's matched before. Okay. Now, what if I had a smarter algorithm? What if I had an algorithm that would actually use the knowledge of the matches that happened before we saw a mismatch? So let's say this algorithm has matched the first 4 A's and is now at this point. So 1, 2, 3, 4, we're here. Okay. And it sees that, well, in S, I have an A character. In T, I have a B character. They don't match. Okay. Now, I want to say that I tried this prefix of S and it didn't work, right? So now I want to go to trying this prefix of S. But these two prefixes are very similar, right? So this other prefix that I want to use already has 4 A's. So ideally, all I want to do is to move this one forward and say, compare this A with this B, because if they match, if this was actually a B, then all of the previous ones have already matched. And I would have a complete match. I wouldn't have to go back and check that all of these A's match, right? So if I had a smart algorithm, it could do something like this. But of course, the naive algorithm has no way of doing this. And of course, this is a very special case where I just had tons of A's. Suppose that instead of having tons of A's, I had a very strange string with many different letters. How could I really know that I already have a long match and I don't have to match from the beginning of my pattern? Okay, so this is the question that is actually answered very nicely by the KMP algorithm. Now, I'm going to do something at the beginning, which is actually, when I think about it, kind of a dynamic programming step, but people don't really look at this as dynamic programming. So here's the thing. I'm going to create a new array, and I'm going to call this LPS. And LPS of I is going to be defined like this. I'm going to look only at the first I characters of my pattern T. So for now, forget about the string. Let's just focus on the pattern. I'm going to look at the first I characters, and I'm going to ask, what is the longest prefix that is also a suffix? So LPS stands for longest prefix suffix. Okay. Now, this is weird, I know, but it will make sense really fast. So this is going to be the length of the longest prefix of the first I characters of T from index 0 to index I minus 1. Or, okay, now let's say to index I. So the first I plus 1 characters. That is also a suffix of the first I characters. Okay, So when I'm doing LPSI, what I'm saying is forget everything that is happening after index I. Only look at everything from index 0 to index I. Now start matching from both sides. What is the longest prefix that you can find that is also a suffix? That's what I want. So let's actually create it for this string t. Oh, and by the way, this longest prefix that is also a suffix, I'm going to add one extra condition here as well. It cannot be the entire string. So what is the longest like strict prefix? It shouldn't be the first I characters itself. Okay. So let me do this. So I have my string t. It's let me change it a little bit. A B. Let's say B A B. Or 2 is enough. A B B A. Okay, let's do this. Okay. What is LPS 0 here? LPS 0 means that I don't look at this part of the string. I'm only looking at this one character A. And I'm asking what is the longest suffix that is also a prefix? Well, in this case, it's of length 1, but I cannot take everything. So I'm asking what is the longest prefix that is not everything, which is also a suffix. So that would be of length 0. Okay, so actually my LPS array is going to start with 0. Now for index 1, and let me just write my indices here as well. 2, 3, 4, 5, 6, 7, 8. For index 1, I have this. I have AA. What is the longest prefix that is also a suffix? It's just A. So what is its length? Its length is 1. Okay. Now for index 2, I have AAB. What is the longest prefix that is also a suffix? So A is a prefix, but it's not a suffix. AA is a prefix, but not a suffix, and so on. There is no prefix that is also a suffix. So here I have 0. What about 3? So if I have only this string, what is the longest prefix that is also a suffix? Is it again 0? I think yes, it's again 0. What if I have this? What is the longest prefix that is also a suffix? It's just A, right? So its length is 1. What is the longest prefix that is also a suffix? It's AA. So the length is 2. What is the longest prefix that is also a suffix? AAB. Okay. So here the length is 3. What is the longest prefix that is also a suffix? AABB. As you see, it's a prefix and it's also a suffix. And by the way, they don't have to be disjoint. It might be that there is a character that is both in the prefix and the suffix. That's also fine. Right. So in this case, I have 4. And finally, for C, what is the longest prefix that is also a suffix? I don't have any. It's just 0. So this is the array that I want to calculate. I want to find this LPS. Now, I have to explain 2 things to you. The first thing is, how do I even calculate this? And the second thing is, why do I bother with this? How is it going to help me in doing my pattern matching? So let me first do the first thing. How do I find this LPS array? Now, a naive way would be to just try to match prefixes and suffixes, and then you would probably get a runtime of m squared, or in some cases I've seen students do m cubed. That's actually impressive in some sense. But remember, we want to do everything in linear time. So ideally, I want to calculate this LPS array in OM. the length of my pattern. Okay. Now, how would I do that? Well, here's what I'm going to do. I'm going to say, let's start with my string T and again, my LPS array. So actually, let me just copy it from here. I have my string T and I start with my LPS array. And well, LPS of 0 is always 0. I know that, right? So here's what I'm going to do. I'm going to do a 2 pointers algorithm, and I'm going to have a pointer pointing to characters in T, and I'm going to have another pointer pointing in my LPS array. Okay. So I'm going to have a pointer here. I call it I, and I'm going to have a pointer here, and I call this one, let's say, P. Or actually, I think on Wikipedia it was called previous LPS. It was called this prev LPS. Okay. So the idea here is that my I is the value, is the index for which I want to compute the LPS value right now. And this previous LPS is just pointing to the previous LPS that I've seen. Okay. But now you will see that the way I move these pointers is going to be a little bit weird. Okay. So this is kind of an algorithm that whose correctness is based on induction. So when I'm at index I, I'm going to assume that the LPS value for all the indices before I are computed correctly already. And I'm going to use them to compute LPS of I. Okay. So let me do some casework here. And I'm going to just write my pseudocode here. I'm going to start by saying that my I is 1 and my P is 0. Okay. And by the way, my P, it's not really the index. My P is the actual value here. Okay. So my P is 0, my I is 1. And here's what I'm going to do. I'm going to say for every I, so as long as I is less than or equal to N, I want to try to find LPS of I. But how do I find LPS of I? So let's see what I know when I'm at index I. This is my string. This is, let's say, my string S. And let's say that I'm at some index here. Let's say I'm reading some character X, and this character X was at index I. Okay. This means that I have already calculated LPS of I minus 1. So if I only had the string up until before this X, I know what is the longest prefix that is also a suffix. Let's show that in a different color. Let's show it in orange. So I have something here. Let's say this is a prefix, and it's also a suffix. So exactly the same string is appearing in these two places. Okay. Now I have this X here. Now, a very happy coincidence would be if I look at this index here and I see an X there as well. Because if I see an X here, then the orange parts match, and of course the X's match. So now I have a longer LPS. I have a longer longest prefix suffix. So this is the first case that I'm going to do. I'm going to say if these two match. So if SI is equal to S, what is this index? What is it? It's exactly this previous LPS, right? Because my indices started from 0. I don't even need +1 or -1 or anything. So I can just say if SI is equal to the S at the previous LPS location, then easy. I just say that basically LPS of I becomes the previous LPS plus 1, right? Now, because I've solved I have to go to I plus 1. So I have to move my pointer on my string forward. So I say increase I. But also, I have to now increase my previous LPS, because my new LPS value is 1 more than the previous LPS value, and I'm keeping track what was the last LPS value that I've seen in my algorithm. Okay. So this is pretty easy. Let's see what we can get from this here. So my previous LPS is 0. My I is 1. I'm going to compare. Is A1 equal to A0? Sorry, is T1 equal to T0? I wrote S. Wow. Sorry, these are all T. Right, I'm doing this on my pattern. Sorry, I forgot. I just write S for all the strings. So these are T. Okay. Now my string name is T. So is T1 equal to T0? Yes, it is. So I would just say that the LPS is 1, and I would increase my I, so I would go to match the next character, and my previous LPS is now also 1. Okay. Again, the previous LPS is the value, it's not the index. Okay. So I don't know, in this example, it looks like the indices and the values constantly happen to be the same, but the previous LPS is the value that is saved in the LPS, not the index. Okay. Now, my previous LPS is 1. My current character in T, the character at index 2 is B, but the character at index 1 is A. So now I don't have that nice case anymore. So basically, when I go to I equal to 2, I have a character at index I which doesn't match this character here. Okay. What can I do? So the first thing I want to check is if I even had a previous LPS, or was my previous LPS already 0? Okay. So suppose that my previous LPS was 0, which means that the length of this orange part here was 0. Okay. What would that mean? So I have this T. Okay, let me just do this again. I have my entire string T. So this one was case 1, this is case 2. And I'm at index I, I'm trying to match the character X. And my previous LPS was 0. Okay. But remember, when I checked whether TI is equal to T previous LPS, the answer was no, they're not equal. So my string does not start with an X. My string starts with some other letter. Let's call it Y, because otherwise it would have been caught in the previous case. Okay. So I had nothing that was both a prefix and a suffix of the first I minus 1 characters, or first I characters actually before index I. So I didn't have this orange part at all. And these two letters are also not matching. What does that tell you? What is the longest suffix that I can find here? That is also a prefix. I can't find anything, right? It's 0. Tell me why. I don't have a prefix of length 1 that is also a suffix, right? Because Y doesn't match S. Why can't I have a prefix of length 2 that is also a suffix? Because if I had that, what would it mean? It would mean that I have an X here, and the X is supposed to match this one, which means that I should have Y here. which means that my previous LPS had to be 1, right? And so on. Generally, I cannot have a prefix of any length that is also a suffix, because the same thing would happen, just with more letters. Okay, so in this case, I can safely say that my LPS is 0. So going back to my pseudocode here, I say if previous LPS was 0, then I know that LPS of I is also 0, and I just move forward to the next I. Okay, so increase I, go look at the next one, and I don't have to change previous LPS because it was 0 and it's still 0. Okay. The interesting case is when this orange part, the part that matched before, is not of length 0, but then the character also doesn't match. So I'm going to put it here. This is, let's say, case 3. It's pretty much like case 1, except that the character doesn't match. So I have this. And here, let's say I have a different character. I have a character Y. Okay. So remember that the orange part is the longest prefix of the of everything that comes until index I minus 1, which was also a suffix. So the orange part is appearing twice, once before Y and once before X. Okay. Now X doesn't match Y. What can I do about this? Now, this is the part where the algorithm is really genius. It says, let's just look at this orange thing. And this orange thing is shorter than the string that I have right now up until index I, right? So I have calculated an LPS for this orange thing as well. Right? So at some point in my algorithm, when I was calculating the LPS, I calculated the LPS for this orange part. And let me show that LPS in a different color. Let's use red. So let's say this was the LPS of the orange part. So it's a prefix of the orange part that is also a suffix of the orange part. But remember, the orange part is appearing twice. So I have the same red thing here and here as well. Okay. Now, here's the question. After this first red one here, do I have an X or not? So the question is, go look here and see, is there an X here? Because if there is an X there, then I can match it with this X, right? And now I can say I have a prefix, the red part plus X, which is also a suffix, the red part plus X. Okay. But can I possibly do better than this? Can I find a prefix that is also a suffix and is longer than the red part plus X? No, because imagine that I have that, right? Imagine that I have something. Let's say I have, now let's do the green thing. Let's say I have a green thing followed by X, and let's say that green thing appears here followed by X as well. So what does this mean? This means that the green thing appears at the beginning of the orange, and it also appears at the end of the orange. Remember, these two oranges are the same. So the green thing should be shorter than or equal to the red by definition, because the red part was the longest prefix of the orange part, which is also a suffix. Okay. So this makes our code super easy. And this is really weird. So this is my third case, my else part. And it's literally one line of code. It's this. Previous LPS becomes LPS of previous LPS minus 1. That's it. This is exactly, I mean, the code looks weird, but this is exactly this intuition here. So the idea is that I was trying to match these orange parts, but then I saw that this orange part is followed by a Y and this orange part is followed by an X. So now I know that the maximum thing that I can hope to match is the red part. So I just try to match the red part now. If I can match it, if there is an X after the red part, I'm happy. If I cannot match it, I have to do the same thing. This red becomes orange and I have to go back. So the only thing I have to do in this case is that I don't touch I because I haven't found the answer for index I yet. I just change the value of my previous LPS, and this one, LPS of previous LPS minus 1, this is just the length of the red part. Right? Because previous LPS minus 1, remember, previous LPS is the length of orange. So previous LPS points here as an index. So previous LPS minus 1 is the last index in the orange. Right? So if I want the length of the red part, it's LPS of previous LPS minus 1. Okay. Awesome algorithm. Now I have all of the cases, and as you see, it's super easy to code. And I didn't even have to do it in C++. What's my runtime? And also, I proved to you that the algorithm is correct while I was explaining, so hopefully that was convincing. But what is my runtime here? And I have another typo here. This should be M because we said that the length of our pattern is M. Look, I basically have 2 pointers or 2 values. I have I and I have previous LPS. Decided to call it previous LPS and not P. And so I starts from being 1 and previous LPS starts with 0. Now, how big can I get? I can increase at most up to n, right? And it increases at this line and at this line. So let's just look at the total runtime at each line. Okay. This part, I++, it's going to be run at most OM times, right? Because my I is only ever increasing and it can only increase to M. And I can say the same thing about this line. This is also OM. So that's what I know about index I. But if this one runs only OM times, then it means that the line before and the line after also run OM times at most. So because they run the same number of times, basically. So this is OM, this is also OM, and this is also OM. Okay. The problem is with this one. This last line. How many times does this last line run? Now, the interesting point is that you can look at the variable previous LPS. When does previous LPS increase? It only increases here, right? So its value starts from 0, and its value increases at most M times. And here, previous LPS is actually decreasing. This is going from the orange to the red. Okay? But it cannot decrease more than we have increased it because it's always at least 0. Right? So this shows that this line is also run at most OM times. Because previous LPS has to first increase in this line before it can decrease in this line. And if I'm increasing it here, I'm doing the plus plus only OM times, then I can decrease it OM times at most as well. So yeah, the total runtime is OM. So this is a linear time algorithm, and honestly, one of the cleverest algorithms I've seen. But this is not done yet, right? So this was just creating our dynamic programming, doing our LPS. Now I have my LPS array. And by the way, I'm not going to do an example here. I'm just going to give you a video. There are tons of videos on YouTube that do examples of algorithms. I don't have time for that. But remember, my main problem was not that. My main problem was that I'm given the string S and the pattern T. The question is T a substring of S? And until this point, I've just created this really clever thing on top of T. But how does it help me? So let me copy this. And actually, let me go here. Let's say this is our pattern matching part. Now, as usual, I'm going to start with having 2 pointers, one on S, one on T. Okay. So I'm going to have a pointer here, which is I. I'm going to have a pointer here, which is J. And if I want to write some pseudocode, so this was the pseudocode of the parts where I calculate the previous LPS and so on, the LPS array. After that's done, I want to actually do my matching. So I start by saying I and J are both 0. Okay, let's say I want to match and I want to see if there's an instance of T in S. The first and simplest step is just check Si and Tj. If they're equal, move both of your pointers forward. Right? So couldn't get simpler than that. And actually, I'm just going to have a while loop here, which says, should I put my while on I or on J? On I, let's say. While I is less than or equal to N, so as long as I have not finished my main text, I'm just going to say if Si is equal to Tj, just increase both of them. Okay. Nice. Now, again, I'm going to do a casework. The next case I want to look at is if if Si is not equal to Tj, and additionally J is 0. So let's say I have a mismatch already at the first character. Okay, so for example, let's say my string S started with a B, right? And I have this. It doesn't match the first character of my pattern. If it doesn't match even the first character, it's hopeless. I'm not going to find anything here, right? So it makes sense to just go forward in my main string S and just ignore the current character. Okay, so if this happens, I say else if J is 0, just increase I. I didn't find a match starting at this particular I or ending at this particular I. No, starting at this particular I, I'm happy with that. Okay. The interesting case again. Let's say I'm doing these matchings. Let me actually just do it here. So I'm starting right like this, and let's say I also have my LPS array. I don't have my LPS array for this one. Do I? No. Okay, sorry. I have to do the LPS before I can do the example for you. So what is my LPS here? It's going to start with 0 and then 1 because A is both a prefix and a suffix, and then 2 because AA is a prefix and a suffix, and then 3 because AAA is a prefix and a suffix, and then 0. Okay, so this is my LPS array. So I'm going to start matching. Does the character in S match the character in T? No. And it's the first character of T. So I give up on my character in S. I say, I don't care about B. I'm going to the next character. Okay. Does it match? Yes, it does. So I move both of my pointers forward. I say now I points to this one and J points to this one. Does it match? Yes. So I move forward. This goes forward. This one also goes forward. Does it match? Again, yes. So this goes forward, and this also goes forward. Does it match? Yes. This goes forward. This also goes forward. Does it match? No, it doesn't match. I have an A in S. I have a B in T. So I have a mismatch. Now, the naive algorithm would just go to the beginning of T. It would just go back to the beginning of T. But I calculated all of these LPS values so that I avoid going to the beginning of T. Okay. Now, what do I know when I'm at this point and things haven't matched? I know that everything before this has already matched, right? So I know that this part, this prefix of T, was equal to this one. Right? That's the reason why my pointers got to that place in the first place. So now that I know these two match, how can I use this idea so that I don't have to go to the beginning of T? Where in T should I jump? Look, what was the thing that I was actually trying? What was the thing that I was hoping? I was hoping that this string would be equal to this string. But it didn't work out. In this case, the last characters were not equal. But I know that this prefix was equal to this prefix. Now, in the naive algorithm, I want to go one character forward. I want to look at this string, right? And again, the same string here. Okay. But what's interesting here? What do you call this color? Okay. I should have used a different color. I don't know the names of some colors. What is this color? Pink? It's not really pink, is it? Okay. It's kind of halfway between pink and purple. Okay, let's say pink. So here's the thing. I have this pink one here, and I also have it here. But I care about the blue one, right? I know that everything in pink has matched. So everything in pink is a prefix of my pattern T. But the question is, how much of blue is a prefix of T? Right? Now, forget about the last character of blue. Just look at this part of pink. I'm asking how much of this is a prefix of T. But pink itself is a prefix of T. So I'm asking what is the longest prefix of pink that is also a suffix of pink? Does that make sense to everyone? Look, pink was a prefix of my pattern T. Now, instead of pink, I'm looking at blue. But I don't want to go to the beginning of T and match again. I want to know how much of blue is already a prefix of T. So if I find a suffix of pink that is also a prefix of pink, because pink itself is a prefix of T, then that suffix is also a prefix of T. Right? So that's what I'm going to do here. I'm going to say, again, this line is going to look so fun. It's just going to say J becomes LPS of J minus 1. Okay. So what's happening here again? Let's go over this example. Oh, it's removing this one, LPS of J minus 1. Okay. Let me remove all of these things. Again, remember, I'm on this B in T, and here I have matched 4 A's, 1, 2, 3, 4, and I'm trying to match this one. So this is when I've seen my mismatch, right? And what I know already is that this pink part is appearing in S, of course, and it's also a prefix of T. Okay. Now I'm saying go to your LPS array and figure out what is the longest prefix of the pink part that is also a suffix of the pink part. And in this case, it has a length of 3. So I say, if I look at a suffix of the pink part of length 3, let's show that in red, this red part. I know that it's also a prefix of pink, but pink itself was a prefix of T, so red is a prefix of T. So I know that I have my red here. So the red in S is matching the red in T. What should I try to match with the next character in S? Well, the character immediately after the red in T. Okay, so what is the length of the red in T? It's basically LPS of J minus 1, right? Because this is like index J, so this one was index J minus 1. LPS of J minus 1 is the longest prefix of pink that is also a suffix of pink. Okay, so red should just become LPS of P minus 1, and I know that the red already matches. Because the red already matches, I should just try to match the next character after the red with the current character in S. So this is all I have. J becomes LPS of J minus 1. And I don't need plus 1 because my indices are starting from 0. Okay. Now, at this point, again, do the two characters match? Yes, they match. So I'm happy. Whenever there is a match, I just move forward. I go here and I go here as well. Let me erase these ones. I'm just going to continue doing this example. Now, at this point, again, they don't match, right? So again, the question is, what is the pink part? The pink part is this. This is what I've already matched. What is the longest prefix of the pink part that is also a suffix? It's just length 3. So basically, again, I have to go back to this character. And I have to check again. Do they match? Yes, they do. So again, I move forward. Do they match? No, they don't. So again, this one goes back to where it was. Do they match? Yes, I go forward. Do they match? No. So, but again, I have this pink one, and I have the pink one here as well, and I have this red one. So I just go back here. Do they match? No. So, but now my pink and red are different, right? So when I'm here, they're not matching, but my pink array is this one. I have matched only 3 A's at this point, and I have these 3 A's. So now my red array would only have length 2. It will only have these 2. And so I will go here. Do they match? No. So I will have to again move back. So I move back here. Do they match? No, I would move back again. And at this point, they don't match, but I'm also in the case where I'm at the beginning of T. And I said that when they don't match and I'm at the beginning of T, I give up on this character in S and I keep moving forward. So finally, I move forward and I ask, do they match? They do match. So I move both of them forward. Do they match? Yes. Move forward. Do they match? Yes. Oh, I put 1 fewer A than I wanted, sorry. So move both of them forward. Do they match? Again, yes. So move both of them forward. Do they match? Yes. Move both of them forward. And by the way, this is when you know you're done. When you end up exceeding your pattern T. When your pointer goes after all of the characters in T, it means that you have matched everything in T, which means you found an instance of T. So that's what I have to add to my code here. I have to say, if at some point I matched everything, that's the end of it. Okay? And the only case that can happen is inside this if when I'm increasing my J. So when J becomes the length of T. But I can also write it outside here. I can just say at the end, if J is equal to M, which was the length of my pattern, this means that I have found a match, I can return true. Or if I want its exact index, actually I'm at the end of this match with my I, right? So I have to return the index of the beginning of the match. So it would be I minus M. Do I need plus 1 minus 1? No. Yeah, it would be exactly I minus. Okay. So this is the KMP algorithm, all of it. Now, the correctness of this part can also be proven in the same way as the correctness of the LPS part. Why is that? Why am I correct with the same argument? Well, first of all, when I find a match, I have definitely matched all of my characters. So if I find something, what I find is correct. But I want to say that if a match exists, I will definitely find it. And again, here I have to just do the case work. If the two characters match, I'm going forward, that's correct. If I can't even match the first character, I increase by 1. And this last case is the only interesting case, really, where we have to prove correctness. And this is exactly like the last case when I was doing LPS. So the situation is exactly like there. Again, if I can just draw this, I have my S here, and let's say I have my T here, and I'm at some index I in S. I'm sorry, I'm running out of time here. And I've already matched some things. So I'm at index J here in T, which means that I've matched everything before index J with whatever came before index I. Right? But now I want to match X with something. If I had an X at index J, I would be happy. That would be my case 1, where I matched and went forward. If J was the first character and there was a mismatch, I knew that I couldn't find a match here anyway. But now, let's say J is not the first character, and I have some character Y here. So the argument is exactly like the last case of LPS. I say that if I want to match something with this X, I should just look at a prefix here, which also appears here as a suffix. But the two orange ones are the same. So if red is a prefix of this orange, it's also a prefix of this one. And if it's a suffix of this one, then it's a suffix of this one. So it has to basically be the longest prefix suffix of the orange. Same argument as before. Finally, runtime analysis. I can only increase n times in the first if here, and also in the second one. So J also increases at most n times, because there are cases where I'm increasing I, but I'm not increasing J, right? So J can decrease at most n times because it only increased at most n times, and it's always greater than 0. So this line is also running O(n) times. So every line here is running O(n) times at most, and every line here ran for O(m) times at most. So my total runtime is O(n) plus m. And I'll see you tomorrow.